Hi everyone, I'm Xinran. Today we present ForkGAN, a novel unpaired image translation network. It is a joint work with Ziqiang Zheng, Dr. Yang Wu, and Dr. Jianbo Xi. Currently, most visual analysis models for self-driving cars are developed on data taken in an ideal situation, such as during daytime on a sunny day. However, we often need to drive under adverse conditions, such as rainy night. The dark background and reflections of rain greatly challenge those models, since they are biased toward a more standard condition. Therefore, we're interested in translating the visual data from adverse conditions to the standard condition, so that it can help us see through the rainy night. Our model should be unbiased toward both data and tasks. This means that it works regardless of the weather and lighting conditions, and the same translation results can be beneficial to various visual analysis tasks at different levels, like localization, semantic segmentation, and object detection. This is a challenging problem which has never been solved before, as far as we are aware of. One may try to avoid it and look for simpler solutions, like collecting more data directly and working on individual vision tasks. However, besides the difficulties of the data itself, annotating such data is very hard and costly, which leads to limited annotated training data. Making use of large-scale, public, and labeled daytime data may ease the problem, but direct usage brings data bias and task bias. To overcome this, one possible solution is low-light image enhancement, such as in LightGAN. It changes the luminosity of the image without altering much of the texture and content. That makes it task unbiased. But it is still biased on certain data contents and only works for illumination adjustment. Another solution is unpaired image translation. Taking the most representative work, Cyclic, as an example. As shown from the image, while it successfully alters the conditions, it often fails to preserve the details and can add artifacts, so that they bias on lower-level vision tasks. A recent model called TodayGAN has been shown effective for boosting the performance of localization. However, both its design and translation results indicate that it cannot generalize well to higher-level vision tasks. Different from existing works, we target an unbiased image translation for linking unlabeled adverse condition data and labeled daytime data, without any pairing assumption. To make the translation unbiased with respect to both data and task, we believe the key is to effectively disentangle the domain-agnostic information, like object position and shape, with the domain-specific information, like illumination, so that fine details can be retained while the weather and lighting condition are altered. Our model is called ForkGAN. It translates image from adverse conditions to a standard condition and significantly boosts the performance of all levels of vision tasks, such as localization, semantic segmentation, and object detection. Next, I'll explain the specific design of ForkGAN through an example of night-to-day translation. Given a nighttime image, a domain-specific encoder extracts its domain-agnostic representation, which is then fed into a fork-shaped generator with two decoders. A reconstruction decoder reconstructs the input image, and a translation decoder alters weather via a Cyclic-style structure. A similar model is designed for the day-to-night translation. So how exactly does ForkGAN serve our purpose of disentanglement? Well, for effective disentanglement, the domain-agnostic information needs to be faithfully retained. This information, such as position and shape of objects, is usually the crucial content that will help later vision tasks. We introduce an adversarial domain classifier in the network. By regularizing its classification laws, we aim to remove domain-specific information. In the ideal case, by looking at the latent representation zx and zy, the classifier should not be able to distinguish the original source domain. The across-translation perceptual loss also ensures that domain-agnostic information is retained. Through training, ForkGAN learns 2 domain-specific encoders, 2 translation decoders, and 2 reconstruction decoders. When using ForkGAN for night-to-day translation, we can have the input image sequentially go through the night domain encoder, day domain translation decoder for initial translation, followed by the day domain encoder and day domain reconstruction decoder as shown here, which leads to our inference network. During the inference stage, we first pass the image through the translation branch, and then reuse the trained reconstruction branch to add more realness to the translated image. Note that the translation procedures from day to night and night to day are totally symmetric, so we do not bias toward a particular domain. We also don't introduce any loss function that is specific to certain vision tasks, so the model is also task-agnostic. Now we demonstrate some experiment results of multiple vision tasks with the help of ForkGAN. For the experiments, we use mainly 2 datasets. The elderly dataset has GPS-tagged images and can be used to evaluate localization performance. It contains images collected at rainy nighttime that are blurry with a lot of reflections. The BDD100K dataset contains ground truth for semantic segmentation and object detection, with images taken in both daytime and nighttime. In the localization task, we use FID as an indicator of image translation quality. Lower FID means smaller distance between the real sample distribution and the generated sample distribution, and thus better translation quality. For localization, we use the sift features. Larger value indicates better localization performance. For benchmarking, we include EnlightenGAN, which uses image enhancement method to strengthen the signals from nighttime. We also include unpaired image translation models, such as Cyclic. We're particularly interested in comparing our performance with TodayGAN, which is an image translation model that also targets self-driving in nighttime. As we can see from the table, ForkGAN gives the best translation quality and also the best localization performance. For semantic segmentation, we again use FID to indicate translation quality and the standard MIOU for segmentation performance. From the table, ForkGAN has the lowest FID and the best segmentation performance. Here are some image translation results on the elderly dataset and on the BDD100K dataset. We see that when a nighttime image is translated to daytime by ForkGAN, the semantic segmentation performance is greatly improved. For object detection, given the limitation of labeled training data, we perform experiments in 2 settings. In the first setting, only daytime annotation is available. In the second setting, both daytime and nighttime segmentation labels are available. In both cases, we use ForkGAN to perform day-to-night translation to achieve data augmentation. Therefore, we can reuse the labels from daytime images. For testing, we're only evaluating on nighttime images. For comparison, we also use TodayGAN for data augmentation and evaluate the detection results by training the same faster RCNN model. As we can see from the chart and the visualization results, ForkGAN brings better detection performance in both scenarios. During our experiments, we noticed an interesting failure case. It usually happens when there's a black car in front of us and is usually ignored after translation. We think this might be due to the lack of visual cues to separate the contour of the car with a dark background. To conclude, we propose a new unpaired image translation model, which is unbiased with respect to data and tasks. The key for its effectiveness and superiority is the fork, which enables both representation disentanglement and complementary refinement. Thank you so much for listening to our presentation.